Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from NVIDIA ToolOrchestra, Elevating Intelligence via Efficient Model and Tool Orchestration. Large language models have made impressive progress, but they still fall short on the hardest multi-step reasoning tasks, such as those in humanity's last exam. The common approach today is to use a single, very large model, sometimes with a few tools like web search or a code interpreter. This can work well, but it's extremely expensive and not always efficient. The core goal of this paper is to show that we can actually push the upper bound of intelligence while significantly reducing cost and latency by rethinking how we structure tool-using AI systems. The paper introduces ToolOrchestra, a method for training a relatively small orchestration model that manages a collection of tools and other language models. Instead of relying on one giant model to do everything, an 8 billion parameter orchestrator decides when to reason on its own, when to call specialized models, and when to use external tools. Crucially, this orchestrator is trained with reinforcement learning to optimize not just for task success, but also for efficiency and alignment with user preferences about which tool should be used. At a high level, Orchestrator takes a user task and solves it through multiple turns. In each turn, it can either continue reasoning in natural language or decide to call a tool. The tool set includes basic utilities like web search, domain-specific functions and code interpreters, specialized language models for coding or math, and powerful generalist models like GPT-5 or Claude Opus. Through reinforcement learning, the orchestrator learns when and how to use each of these resources, forming dynamic tool use strategies tailored to each problem. The paper makes 4 main contributions. First, it proposes ToolOrchestra, a reinforcement learning framework for training orchestration models that coordinate diverse tools and LLMs. Second, it introduces Orchestrator 8B, a relatively small model that outperforms much larger systems on challenging benchmarks. Third, it designs a multi-objective reward scheme that simultaneously optimizes for task outcome, computational efficiency, and user preferences over tool usage. Finally, it presents ToolScale, a large synthetic dataset of complex user-agent-tool interactions that supports effective reinforcement learning for these orchestrators. The authors evaluate Orchestrator 8B on 3 demanding benchmarks: Humanity's Last Exam, Frames, and Tau2 Bench. These benchmarks stress deep reasoning, multi-step planning, and tool use. Orchestrator 8B not only matches but surpasses GPT-5 in accuracy on these tasks, despite being much smaller. Importantly, it does so at a fraction of the cost, demonstrating that a well-trained orchestrator over tools can be both more capable and more efficient than a monolithic large model. Looking at the numbers, Orchestrator 8B achieves 37.1% accuracy on Humanity's Last Exam, compared to 35.1% for GPT-5. On frames, it reaches 76.3% versus GPT-5's 74.0%. On 2Bench, it scores 80.2%, again ahead of GPT-5 at 77.7%. These gains come with substantial efficiency improvements. On HLE, Orchestrator is about 2.5 times more cost-efficient, and on Frames and 2Bench, it uses only around 30% of the cost of GPT-5-based systems. A key observation is that off-the-shelf or even RL-trained models, when prompted to use tools, tend to over-rely on a single strong model. For example, GPT-5 tends to call GPT-5 Mini most of the time, and Qwen 3 8B frequently delegates to GPT-5. This leads to high costs and underutilization of specialized tools. In contrast, Orchestrator 8B learns to distribute its calls more evenly across the available tools and models, using each where it is most effective. This balanced tool usage is a major factor behind its superior cost-effectiveness. The authors analyze tool calling statistics across different models acting as orchestrators. Strong foundation models like Qwen 32B, coding specialized models, and large math models often show strong biases toward particular tools or generalist LLMs. Orchestrator 8B, however, uses a more diverse mix of tools and makes relatively few calls to GPT-5, yet still achieves better overall performance. This suggests that the RL training successfully teaches the orchestrator to exploit specialized tools and reserve expensive generalist models for cases where they are truly needed. When you plot model accuracy against dollar cost, Orchestrator 8B lies on a more favorable part of the cost-performance frontier than monolithic large models. It delivers higher accuracy at significantly lower cost, effectively dominating many existing systems. This demonstrates that orchestrating a set of tools and models with a small, well-trained controller can be a more efficient path to high intelligence than simply scaling up a single model. The authors also study how well Orchestrator 8B generalizes beyond its training setup. On benchmarks like HLE, Frames, and Tau2 Bench that include tools not seen during training, the Orchestrator still performs strongly. They further varied pricing and latency configurations for tools and models, and find that Orchestrator 8B consistently remains the best option in terms of performance, cost, and latency. This robustness indicates that the model has learned general principles of efficient tool use, not just overfitted to a specific tool mix or price list. To support reinforcement learning for orchestration, the authors introduced ToolScale, a synthetic data generation pipeline. For each domain, a language model first creates a domain-specific database and tool APIs that simulate an environment. It then generates a wide variety of user tasks, along with the corresponding golden sequences of tool calls and actions needed to solve them. This synthetic dataset gives the RL training process dense, structured feedback on how an ideal tool-using agent should behave across many domains and scenarios. ToolOrchestra trains the orchestrator with reinforcement learning using 3 types of rewards. Outcome rewards measure whether the task is solved correctly and how good the final answer is. Efficiency rewards penalize excessive cost and latency, encouraging the model to use cheaper or faster tools when possible. Preference rewards encode user or system-level preferences over which tools should be used. For example, avoiding certain APIs or limiting calls to expensive models. By optimizing all 3 objectives together, the orchestrator learns to adapt its strategy to each query, balancing quality, cost, and preferences rather than following fixed heuristics. Beyond accuracy, the authors measure real-world efficiency metrics such as dollar cost and wall clock latency. Across humanity's last exam, Frames, and Tau2 Bench, Orchestrator 8B consistently shows lower average cost and latency than strong baseline systems, including large generalist models. Additional experiments where tool pricing is varied show that the orchestrator continues to make good decisions, preserving its efficiency advantage. This indicates that the learned policy is robust to changes in the underlying economic environment of tools and models. The main takeaway from this work is that a small orchestration model, trained properly, can outperform much larger monolithic language models on complex tool-intensive tasks, while also being cheaper and faster. Reinforcement learning with outcome, efficiency, and preference rewards is key to enabling adaptive, cost-aware tool use. The ToolScale dataset provides the rich synthetic experience needed to train such agents. Looking ahead, the authors envision more sophisticated, potentially recursive orchestrator systems that could further push the upper bound of intelligence and efficiency for real-world agentic AI.